Welcome to question 3 of the 2002 Mathematical Methods Exam 2. In this video we will be looking at the solutions and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. And finally, as we progress through this question, you'll see that there are colour-coded boxes to indicate how likely CAS is to be used in efficiently answering the question. So let's get started. For question 3, part A, we know that we have the polynomial 2x to the power of 4 minus x cubed minus 5x squared plus 3x can be factorised as x times 2x subtract 3 times ax squared plus bx plus c. And we are asked to find the values of a, b and c. And now this question can easily be done using the factorise command on your calculator. So on the CAS calculator, go into the main menu. Next we want to type in the equation for the polynomial, which is 2x to the power of 4 minus x to the power of 3 minus 5x to the power of 2 plus 3x. And now to factorise this, we're going to highlight it and go interactive, transformation, factor, and click factor. And that will give us the factorised form for this expression. So from the CAS calculator, we know that this polynomial is equivalent to x times 2x minus 3, and then the ax squared plus bx plus c was x squared plus x subtract 1. So the question asks to find the values of a, b and c, where a, b and c are the coefficients of x squared, x and the constant term respectively. So therefore, from our factored form that we got from the calculator, a would equal 1, that's the coefficient of x squared, b would equal 1, that's the coefficient of x, and c would equal negative 1, which is the constant term. So that is the answer to this question. For part 2, we're asked to find the exact value solutions of the same polynomial equation equal to 0. So that means that you could solve the factored form equal to 0, and that's something that the CAS calculator can readily do. For part 2 on the calculator, you can drag down either the factorised expression or even just the original one, and we're going to solve that equal to 0. So highlighting that equation, we go interactive, equation equality, solve, and we want to solve for x, so hitting OK will give us our solutions. And just make sure that your calculator's in standard so that you get those exact values. So x equals 0, x equals 3 on 2, and then these two other fractions, which I'll leave up on the screen to copy out now. So therefore, from the CAS calculator, we found that x could equal 0, x could equal 3 divided by 2, or x could equal minus 1 minus the square root of 5 divided by 2, and lastly, x could equal minus 1 plus the square root of 5 divided by 2. So they are the 4 solutions to this question. For question B, we have the diagram below shows the curve whose equation is y equals a half times 2x to the power of 4 minus x cubed minus 5x squared plus 3x. And the normal to the curve at A, where x equals 1, is shown. And for part 1 of part B, we're asked to show that the equation of the normal is y equals x subtract 1.5. So when we're asked to show something, we've got to pretend that we don't know the answer and go and find it. So if you want the equation of the normal at the point where x equals 1, we could start by finding the gradient of a tangent line to that point. So that means we want to find the derivative dy dx, and we want to evaluate it when x equals 1, and that's something we could use our CAS calculator to do. So now on the calculator, we wanted to calculate the derivative when x was equal to 1. And just be aware that the equation slightly changed, so we need 1/2 to be multiplied by this same polynomial here. And now we want to go and calculate the derivative, so we go interactive calculation diff, and we want to actually calculate the derivative at a value, and that value was when x is 1. So we put 1 in this final box, and hitting OK gives us the value of the derivative when x equals 1. And from the CAS calculator, we found that that is equal to negative 1. So just so we can keep track of what we found, this is equal to the gradient of the tangent at the point A. So we know that the normal line is perpendicular to a tangent line, So that means that the gradient of the normal is equal to -1 divided by the gradient of the tangent. So that means the gradient of the normal is going to equal -1 divided by the gradient of the tangent, which was -1. So that gives +1 as the gradient of the normal line. So again, I'll just keep track of what we've found. And now the final thing that we need to find before we can show that the equation of the normal is y equals x subtract 1.5 is we need to know the exact coordinate of A. So we know that x equals 1 is the point where A is located at. So when x equals 1, we find that y is equal to, and we would just sub 1 into this equation. So that's something we'll do on our calculator. So to calculate the value of y when x is equal to 1, we need to make sure we've got our equation in there. So 1/2 times this same polynomial again. And we can use math 3 and this straight up and down line to say given that x is equal to 1. And hitting execute will give the y value for when x is equal to 1. And that was equal to -1/2. So the coordinate of A is going to be 1, -1/2. So now what we're really doing is finding a line with a gradient of +1 through the point 1, -1/2. So we can use the formula y take y1 equals m times x subtract x1 to find the equation of a line. So therefore we'd have y subtract -1/2 is equal to the gradient, which was 1, times x subtract x1, which is 1. And that, when we've solved for y, is simply going to give x minus 1.5. And that was what we were being asked to show. So even though it's a technology active exam, for 3 marks and the fact that we were asked to show what the equation was equal to, we needed to have a fair bit of working involved. Although we did use our calculator a fair bit to assist with some of those calculations. So for part 2 of part B, we're asked to show that this normal, the normal we just calculated, is in fact a tangent to the curve at a point B, and find the exact values of the coordinates of B. And we can see that once again it's a show that question, so we've got to show that that's the case. And for 4 marks, we've probably got to give a reasonable amount of working to answer this question fully. So to start off with, I'm going to set the equation of the chordic function, which is 1/2 times 2x to the power of 4 minus x cubed minus 5x squared plus 3x. We're going to let that equal the equation of the normal line that we just showed, which was x minus 1.5. So we want to solve that equation on the calculator, so we're going to drag down the rule for our polynomial, and we want that equal to x subtract 1.5. And now that's an equation that we want to solve, so we highlight it and go interactive equation inequality solve for x, and hitting OK gives us 3 solutions to when that normal line intersects or is equal to the polynomial. So from the CAS calculator, when that's solved, we get x equals -1, x equals 1, and x is equal to 3/2. So they're the 3 points where that normal line will intersect the curve. And of course, x equals 1 is where we calculated the normal line to be, so that's expected. So one of these other 2 solutions must be B. And having a little bit of a look at the sketch that they've provided, it looks like B is where x is equal to -1. So that's the point we're going to start with. So next up, we're going to calculate the derivative dy dx when x is equal to -1 to see what the gradient of a tangent line at that point would be. Next, we want to calculate the derivative when x is equal to -1. So we highlight the expression for our polynomial, and again we'll go interactive calculation diff, and the derivative this time at the value is when x is equal to -1. Hitting OK, and that gives out a gradient or a derivative value of 1 as well. So from the calculator, we found that that is equal to 1. And again, just to keep track of what we've found, that's the gradient of the tangent line when x is equal to -1. So the gradient of the tangent line is equal to the gradient of the normal line, and they both pass through the point B, so we're starting to show that that normal line is a tangent to the curve at the point B as well. So we can say as both lines share the same gradient and pass through the same point B, they must be the same line, showing that the normal at point A is in fact a tangent to the curve at the point B. Now, that wasn't all this question required us to find. It said find the exact values of the coordinates of the point B. So that's the last thing we have to do for this question. So we knew that the point B had an x value of -1. So that means we can calculate what the y value is. And now on the calculator, we want to calculate the value of y for our polynomial. So we'll drag this down when x is equal to -1. So again, we can use that straight up and down line in Math 3 to substitute x equals -1 in efficiently. And the calculator gives us that that is -5 divided by 2, which means that the coordinate of b is going to be -1, -5 over 2. So along with the working to show that the tangent line and the normal line were the same line, that's the other part of the answer to part 2 of this question. For part C of this question, we're firstly asked to write down a definite integral, the value of which is the area of the shaded region shown in that diagram. So if we want the area between two curves, which is what this is asking for, we do the integral from the lower bound to the upper bound, so the x values between which we're calculating the area. For an upper curve, subtract away the rule for the lower curve. And of course, we're going to integrate with respect to x. So literally by upper and lower, we mean which function is above the other one or has bigger y values. So in this case, from b, which has the coordinate -1, -5 on 2, and we found that in the previous question, to a, which had coordinates +1, -1 on 2, we can see that the upper curve is this purple function here, which is the chordic curve. So that has a rule here. And the lower rule, if I do that in green, is this straight line. And we were asked to show earlier that it had an equation y equals x take 1.5. So using that information, the area is going to equal the integral between the upper and lower bounds. So the lower bound is -1. That's the x value that we're starting our area calculation from. And our upper bound is +1, which is the x value that we stop calculating the area for. And then we put in the rule of our upper function, which is going to be 1/2 multiplied by 2x to the power of 4 minus x to the power of 3 minus 5x squared plus 3x. And then we subtract away from that, and brackets are really important here, the function that was x subtract 1.5, or that straight line that we did in green above. And all of that is going to be integrated with respect to x. So this is the integral that we were asked to write down, which has a value that is equal to the area of the shaded region. For part 2, we're simply asked to find the area of that shaded region, and we're asked to do that correct to 2 decimal places. So on the CAS calculator, we want to enter that integral. So under Math 2, we can bring up the integral symbol, and we want to go from x is -1 to 1, so they were our limits. And then we wanted to have an upper function subtract away a lower function. So just so we get it right, I'm going to put those 2 brackets in. And our upper function was the chordic polynomial, so I'm going to drag that rule down. And then our lower function was the normal line that we found way back in part B, which was x subtract 1.5. And now just to finish off that integral expression, we need to integrate that with respect to x. So hopefully we've put all of that in correctly, and hitting execute and changing this from a fraction to a decimal, because it asks for 2 decimal places, gives our answer. So that area was equal to 1.73 units squared. So that is the answer to that part of the question. So in the examiner's report, it says that the question was generally well done by students. And then part 1 and part 2 of question A were completed successfully by many students, but some surprisingly could complete part 2 but not part 1. Such students did not recognise that the answer to question 3AI, which was to find the factored form, or the values of A, B and C once factorised, could be directly obtained from their calculator using factorization. Most students scored some marks on question 3B, but few students achieved full marks on the second part. To show that instruction is quite frequently used in examinations, and students should be aware of what is required for such a question. In this case, a number of methods were available for successful establishment of the result. The most frequently used was to establish that the normal met again at the point -1, -5 on 2, and that the gradient of the curve at that point was also 1. So that's the process that we did on that previous slide. Many students had difficulty with question 3CI, which was that they needed to find a definite integral, the value of which was the area, and many did not state their answer as a single integral expression. Overall, they did not seem to be familiar with the result that for suitable functions f and g, where f of x is greater than g of x, over an interval a to b, then the area of the region between two curves and the lines x equals a and x equals b is given by the integral, and essentially this is the upper curve minus the lower curve between a and b. And part 2 of question C was completed successfully by many students, but others lost the mark because they did not give their answer to the required level of accuracy, which was 2 decimal places for that question.